So how does what you did last night integrate into what we just talked about with bonding? To answer that question, we're going to get into something called a Lewis structure. So what you went into yesterday in that post-lecture, pre-lecture, whatever you want to call it, was the Lewis dot system for identifying how many valence electrons were around a given atom. And there are two applications for that we can get into directly. One with ionic compounds, which you saw a little bit of in that post-lecture, and one with covalent bonds, which is going to be the primary subject of Friday's class. So coming back, going from Lewis dots again, representing here's my element, here are how many electrons are around that element that are capable of bonding, the valence electrons. A Lewis structure is an extension of this by taking those Lewis dot diagrams for individual elements and showing how those dots, how those electrons ultimately pair up to create create two-dimensional structures for given compounds. Now for ionic compounds, this is usually rather simple. All that we show in a Lewis structure is how those electrons move from one point to another. So in the case of sodium chloride, we see that this valence electron in the sodium moves to the valence shell of the chloride. And so sodium is now one electron deficient, so it has a sodium +1 charge. And the chloride has this extra electron now, so it has a 1 negative charge. And the two charges are ultimately what attract each other electrostatically, according to Coulomb's law, to make the compound. I asked you, as part of your preparation today, we were going to start working out of this packet right here. And we're going to start doing some of these exercises regarding Lewis structures. Now, when it comes to doing these kinds of exercises, we want to keep in mind that there is a process involved here. The first step in our process is we need to determine the number of electrons in our molecule. This is one of the places where our knowledge of Lewis structures, those Lewis dots, how many valence electrons we have, really plays a role. Because we can look at a chemical formula and we can say, okay, it's got carbon, carbon has 4 valence electrons, it's got oxygen, oxygen has 6 valence electrons, I can add those together. Our second step getting ahead of myself, is to determine the center atom. Now, there are a number of ways of doing this. Again, Lewis dots tend to help us the most here. We can either do it by evaluating the most unpaired electrons in a Lewis dot structure, or by evaluating the least electronegative element. Now, electronegativity was not a periodic trend that we talked about in chapter 3. It's one that we are going to talk about on Wednesday next week when we talk about bond polarity and bond enthalpy. But the general trend is this. Of our elements on the periodic table, electronegativity, the ability of an atom to draw electrons to itself, increases with nonmetallic character. The more nonmetallic something is, the more electronegative it is. The most nonmetallic element is fluorine. Now you'd say, well, what about the noble gases here? Well, the thing that we have to consider, electronegativity is the ability of an atom to draw electrons to itself in a chemical bond. Noble gases don't form chemical bonds. They're inert. So of those, fluorine, oxygen, and nitrogen are the most electronegative. And then it kind of goes just in order from distance from fluorine. So chlorine is less electronegative than fluorine, sulfur is less electronegative than chlorine, phosphorus is less electronegative than sulfur, and so on. Now, these two principles usually kind of coincide with one another. The least electronegative element also tends to be the one that has the most unpaired dots. Another hint that we are usually given the center atom is usually the element that is listed first in the formula. Not always the case. Not always the case. So hydrogen, for example. Hydrogen is listed first in a lot of different compounds. Hydrogen is never the center atom. Why is it never the center atom? Well, consider it. It's got one valence electron in an energy level that can hold 2 electrons. So at maximum, it can form 1 bond. If I've got a compound with 5 different atoms in it, hydrogen can only bond to 1 of them. It's not going to be the one that's in the middle. Third step. Draw the simplest structure. And the simplest structure is this. The center atom attached to all other atoms using single bonds. So we will always start with this simplest structure with all single bonds first and foremost. And we will end that simplest structure by fulfilling the octet rule for all of the atoms by using pairs of electron dots. So a bond counts as 2 electrons. And so what I do, I count up all the bonds that a given atom is making, and however many electrons that is, I add dots until that number is 8. The last step is to evaluate. If the number of electrons in the structure equals the electron count in our step 1. So step 4, our evaluation is a comparison of our structure to the first electron count that we did. If the two are equal, then we're done. We've created a valid Lewis structure. Now, it may not be the best structure. We can get into some of those finer details as we go, but will at least be one that makes sense. If the number of electrons in the structure is greater than the electron count in step 1, we need to add more bonds. And remove extra dots. The rule of thumb one new bond is going to lower our electron count by 2. So if I have 2 extra electrons, I need 1 more bond. If I have 4 extra electrons, I need 2 more bonds. If I have 6 extra electrons, I need 3 more bonds. The last if statement, if the number of electrons is less than the electron count, we need to add more dots to the center atom. And this one comes with a particular caveat if the center atom is able to break the octet rule. And the rule for breaking the octet rule is that we have to have an energy level greater or than or equal to 3. Because what happens once we get into the 3rd energy level? What kind of orbital becomes available? D. And so the addition of that D sublevel, which for most atoms would be empty, allows for an extra 10 electrons to be potentially added should the need arise. So with that in mind, let's go ahead and look at these structures and start to build them based upon those rules that we just set out. And so we'll start with some simple examples and we'll build our way to more complex. And as we build our way to more complex, we'll start to introduce other concepts that play a significant role in our building of molecules. So let's start with water, H2O. Now hydrogen, alkali metal, has one valence electron, but there are two hydrogen atoms. Oxygen in group 16 has 6 valence electrons. I add those together. I have 8 valence electrons in total to work with here. Once again, we're only concerning ourselves with valence electrons because those are the ones that actually make the bonds. The other 2 electrons in oxygen, the ones in the first energy level, we don't worry about them because they're core electrons. They're not going to actually interact and make bonds. Now, hydrogen can never be the center atom, so it's going to be the oxygen. So I put oxygen in the middle for my simple structure. I draw single bonds to each hydrogen. To complete the structure, I need to fill out the octets. Hydrogen has 2 electrons, and that's all that it needs. Hydrogen doesn't actually obey the octet rule. It obeys something called the duet rule because first energy level only requires 2 electrons, and that's all that hydrogen has is the first energy level. So the hydrogens are okay. Oxygen, I've got 2 electrons here and 2 more here, that's 4. I need 4 more to get to an octet. So I put those in as pairs of dots. And now I have 8 electrons around this oxygen. It now is obeying the octet rule. So there we go. We've done steps 1, 2, and 3. And for this structure, again, pretty easy because, well, it's a simple molecule. Now we go to the last step, evaluation. I have 8 electrons that I'm supposed to have. How many are in my structure? Each bond is worth 2. Each pair of dots is worth 2. 2, 4, 6, 8 in total in the structure. The numbers match. So I'm done. Not too bad. Let's look at a slightly more complicated example. Oxygen. The oxygen molecule, O2. I've got 6 valence electrons per oxygen for a total of 12 oxygens over, or excuse me, 12 electrons overall. Now, when I have only 2 atoms, we don't really need to concern ourselves with the center atom because, well, neither of them are really the center. So I'm just going to draw both oxygens here with a single bond in between. And now I'm going to fill out their octets. Each of these oxygens has 2 electrons from that single bond. So they're each going to need 6 dots to fill out their octet. So 6 for this oxygen. 6 for that oxygen. There's my simple structure. Now, how does it look? Well, I've got 2, 4, 6, 8, 10, 12, 14. 14 electrons in this structure. I'm only supposed to have 12. So I've got a problem here. Go back to our rule of thumb. For every 2 electrons over, I need 1 more bond. 14 minus 12 is 2, so I'm 1 bond short. So I'm going to redraw this with an extra bond between the oxygens, since that's the only place that it can go. And let's see where that takes us. Well, now each of these oxygens has 4 electrons from the 2 bonds. I only need 4 more on each side to fill out the octets. Now each oxygen has 4 in the bonds, 4 in dots, 8 in total. I evaluate 2, 4, 6, 8, 10, 12. This structure now has 12. That matches this 12. This is our correct structure for oxygen. All right, any questions with either of these two? All right, let's skip PF5 for a minute. And let's talk about nitric acid, HNO3. Now, acids are a little bit tricky. In acids, what we are going to have essentially are 2 center atoms, because the hydrogen in an oxoacid is going to bond to the oxygen, or at least one of the oxygens, and not the nitrogen. So if we're evaluating 1 for the hydrogen, 5 for the nitrogen, and 6 times 3, 18 for the oxygens, we get a total of 24 electrons necessary for nitric acid. Now, of the elements that are listed there, hydrogen is actually the least electronegative, so that does us no good. But if we think about our Lewis dots, if I'm comparing nitrogen and oxygen, I can see that nitrogen has 3 unpaired dots. Oxygen just has the 2. It's going to be the nitrogen that is going to be the much more likely candidate. So nitrogen is going to be my center atom. But I also know that I'm going to have an oxygen attached to a hydrogen as one of the spokes of that wheel. Because in acids, if there's an oxygen involved in the acid, the hydrogen is going to attach to the oxygen and not to the other atom. So my simple structure is not as simple as some of the others have been. It's just got that extra little wrinkle that we have to concern ourselves with regard to the hydrogen. But if we keep going with this oxygen has just that one bond, so 2 electrons. It needs 6 more in order to finish. This oxygen up top is in the same scenario. 2 in the bond, so it needs 6 dots to finish. This oxygen on the right-hand side, it's got 2 electrons in this bond and 2 in this other bond to hydrogen. It only needs 4 more. And the nitrogen only has 3 bonds, 6 electrons, so it needs a pair as well. So we've got a lot of electrons floating around here. The question is, do we have 24 electrons? And that's where we have to evaluate. So starting on the bottom, 2, 4, 6, 8, 10, 12, 14, 16, 18 on that nitrogen, 20, 22, 24. This structure has 26 electrons in it. Now we can see that doesn't match. 26 electrons in the structure, we only are supposed to have 24. Where does it go? We need to put in an extra bond. But where does that extra bond go? Now, to answer that question, this is where, again, the Lewis dots kind of come in handy. Because the Lewis dots represent kind of the ideal number of bonds for a particular item. And so I can look at nitrogen. Nitrogen ideally would only have 3 bonds. But we know that that's not going to be the case in this scenario. We're going to have to create a 4th bond between nitrogen and one of the oxygens. The oxygens ideally would have 2 bonds. And so from that standpoint, this oxygen right here already has 2 bonds. It's not going to want to add a 3rd. These 2 oxygens only have 1 bond. So they're going to be willing to add a 2nd. Which one does it go to? Does it go to the top oxygen, or does it go to the oxygen on the left? Right. How many say top oxygen? How many say oxygen on the left? All right. Well, you're both half right. What we're exhibiting here is a phenomenon known as resonance. And so I'm going to flip over to my PowerPoint here for just a second to show off that particular phenomenon. Resonance is exhibited anytime we can create 2 or more equivalent Lewis structures. So in the case of the nitric acid, the choice of top oxygen getting a double bond and left oxygen getting a double bond was completely arbitrary. And when that is the case, we have to understand that the correct answer is neither, or the correct answer is both. And the reason why it's neither and both is because the reality is This two-dimensional structure that we are drawing is just a representation. The reality is resonance structures exhibit something called delocalization of electrons, meaning that that pair of electrons bounces between the two bonds that we are debating arbitrarily over. And so that pair of electrons is neither in the top position or the left position. It's in both positions at the same time. It's in neither position at the same time. Those two electrons are being shared by those two sets of bonds simultaneously. To the point of, if we actually evaluate the size of those bonds are equivalent in length. Those bonds are equivalent in strength. And what's even funnier is that those bond lengths and those bond strengths are somewhere between a single bond and a double bond in terms of overall strength, in terms of overall length. So how do we go about drawing that Lewis structure to show that resonance? So we know this isn't the correct answer. What is the correct answer? Well, the correct answer is going to show the movement of that double bond by drawing both structures simultaneously and connecting those structures with arrows. So that is the correct way of showing resonance in a structure. And again, resonance is coming in because the placement of that double bond is completely arbitrary. And so one of the other ways to show that resonance, to show delocalization, there's a third way to draw this. And you will see this from time to time. Delocalization is often shown as a dashed line that covers the areas that are sharing those extra electrons. So we're showing a single bond for each and a partial double for each as well. Now, if you're asked to draw Lewis structures or resonance structures for like a quiz or exam, go this direction, show the double-headed arrows, show the different structures as they are, just to avoid some confusion. I show you this just so that you don't get confused by it if you see it in your textbook or if you see it on a smart work problem, because it is common to see it that way. Especially when we get into organic molecules, organic chemistry, where there's a lot of resonance possibilities, that becomes even more common there. All right, let's do one more example. And then we'll call this a week. I'm going to skip ahead and do OCS. OCS. So I've got 6 electrons for oxygen. I've got 4 electrons for carbon and 6 for sulfur. All told, 16 electrons. In this structure. Now, of the 3, Carbon, oxygen, and sulfur, we can clearly see carbon is the furthest away from fluorine, is the least electronegative. If we draw the dot structures out, we also see that carbon, since it's in group 14, has 4 valence electrons and they are all unpaired. So if you see carbon in your structure, there's a good chance it's a center atom. Carbon and silicon, germanium, all have that characteristic in common. 4 unpaired electrons, capable of forming lots of different bonds. So if I start with my simple structure, carbon in the middle, single bonds to oxygen and sulfur, I fill out my octets. I end up with this simple structure here. I add it up: 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. There are 20 electrons in this structure. Now, comparing 20 to 16, I know I've got 4 extra electrons, which means I need to make 2 more bonds. And so with 2 extra bonds, I have 3 potential structures that I can draw that would satisfy this problem. I could have a triple bond between the oxygen and the carbon, and a single bond to the sulfur. I could have a triple bond to the sulfur and a single bond to the oxygen. Or I could split them evenly. In all 3 cases, I meet the minimum criteria. But only one of these structures is actually correct. This is not an example of resonance because the pick here is not arbitrary. Oxygen and sulfur are different atoms. They're different elements. They have different wants and needs for electrons. So which one of these is correct? To evaluate it, I have to go to something else. I have to go to formal charge. Formal charge is calculated in these kinds of scenarios. The way that we calculate formal charge is on an individual atom in that molecule. And it's the number of valence electrons that it should have, minus the number of electrons in lone pairs, which for purposes of clarity and easiness, we're just going to call those dots, and the number of bonds. So valence electrons minus dots minus bonds gives you the formal charge for a given atom. Some general rules for formal charge. The sum of the formal charges has to equal the sum, or excuse me, the charge on the species. So if I have an ion, then it's going to equal the charge of the ion. If I have a molecule, all the formal charges will cancel out to equal 0. Formal charges should be minimized as much as possible. So we should be seeing zeros in as many places as possible. Finally, when zeros are not possible, the negative charges should go on the most electronegative atoms. Again, that kind of should make sense. We were doing the molecule drawing on this piece of paper, and we came to OCS. And we recognized at the end of Friday's lecture that the simple structure for OCS with its 20 electrons was far more than what was actually allowed in OCS, only 16. So we knew based on our rule of thumb, we were going to have to add 2 more bonds. The question was, where do we add those 2 bonds? How do we add those 2 bonds? Do we make triple bonds, or do we make a pair of double bonds? And the answer to that question came down to a particular concept. The concept in question was something called formal charge. And if you recall from Friday, formal charge is the number of valence electrons for an individual atom minus its dots minus its bonds. And the key to formal charge is that it needs to be minimized wherever possible. So if I look at these 3 structures, I can see that carbon is pretty common in all of them. Carbon is the same in all of them, in fact. If I look at the formal charge for carbon, I will see that carbon has 4 valence electrons, no dots, and 4 bonds. Regardless of the structure, carbon has 4 bonds. Whether they're 2 double bonds or a single bond and a triple bond, it's still 4 bonds either way. 4 minus 0 is 4. 4 minus 4 is 0. There is no formal charge on any of the carbons in any of the molecules that we drew. Now, oxygen and sulfur are both in the same group. They both have 6 valence electrons. Their formal charge, therefore, is going to be based upon whether they have a single bond, a double bond, or a triple bond. If they have a single bond, 6 valence electrons charge, 6 dots, and in structure 2, that means that this oxygen has a -1 charge. If they are doubly bonded, like in the third structure, I have 6 valence electrons minus 4 dots minus 2 bonds. 6 minus 4 is 2. 2 minus 2 is 0. Oxygens and sulfurs that are doubly bonded have no formal charge. So in the third structure, we would have no formal charge on the oxygen, no formal charge on the sulfur, and we've already established no formal charge on the carbon. So no charges anywhere in this molecule. For the triple bond, 6 valence electrons, 2 dots, 3 bonds. 6 minus 2 is 4. 4 minus 3 gives me a +1. So the oxygen in the first structure has a positive charge. The sulfur in the second structure has a positive charge. So of these 3 structures, which structure do I have formal charge at a minimum? Which one has the most zeros? It's the third structure, right? This is our correct structure. The double bonded structure is the correct structure here because from a formal charge standpoint, none of the atoms have a formal charge. And since the molecule itself is not charged, none of them should have a formal charge. Now, there are some cases where formal charge is unavoidable. Take your nitric acid, for example. If I follow the same kind of guidelines, I'm going to notice that I have a positive charge on the nitrogen and a negative charge on whichever oxygen is single bonded. That's unavoidable. And the reason why it's unavoidable is nitrogen and oxygen are incapable of breaking the octet rule. So since they can't break the octet rule, they're just going to kind of have to make do with whatever bonds that they can make. Now, this formal charge is stabilized by the resonance. That does help a lot. But nonetheless, there is formal charge there. How do I evaluate these 2 structures? Well, it ultimately comes down to electronegativity. The structure that is more favorable is going to have the negative charge on the more electronegative atom, which would make this structure with the oxygen having the negative charge more favorable than if it were the opposite. Now, like I said, neither of them are correct. But if this one wasn't an option, we would still choose the bottom structure over this top one because of where the negative charge lies and the ability of that oxygen to stabilize that negative charge with its electronegativity. So any questions about OCS? Okay, so let's go to PF5 then. Now, PF5 presents an interesting problem. I've got 5 valence electrons for the phosphorus, and I've got 7 for each fluorine for a grand total of 40 electrons. Now, if I draw this structure to obey the octet rule, I end up with something like this. I can only make 4 bonds with the phosphorus to fluorines. I'm gonna have to kind of make like a bridge to get that 5th fluorine in there. If I fill out all of the dots, I run into another problem. Number of electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38. There are only 38 electrons in this structure. So in order to build off of this structure, to get the correct number of electrons, I'm going to have to break the octet rule somewhere. If I follow my guidelines, it would say that I need to have the extra pair of electrons on that center atom. And if I do so, from a formal charge standpoint, I have phosphorus, 5 valence electrons, minus 2 dots and 4 bonds. That's a -1 charge. If I look at this fluorine, I have 7 valence electrons, minus 4 dots and 2 bonds, +1 charge. And this is problematic also. It puts a positive charge on a fluorine atom. Now, as we know, fluorine is as electronegative as they come. Fluorine does not do positive charge. Fluorine either does neutral or it does negative. It doesn't do positive. So this structure has some problems of its own right off the bat. But it brings us to an overall point that we need to make. The question is this: when is it okay to break the octet rule? Now, we've kind of brought up the octet rule as this hard and fast scenario where everything's trying to get to 8 electrons all of the time. And the reality of the situation is that that's not always true. Sometimes it's not possible, and other times it's just difficult. So for example, if I have an odd number of electrons, classic examples of this are nitrogen group substances, things like nitrogen monoxide, nitrogen dioxide. In those cases, I'm going to end up with an odd number of electrons. Nitrogen monoxide, for example, 5 electrons from nitrogen, 6 from oxygen, 11 in total. It is literally impossible to get an octet for nitrogen and oxygen with only 11 electrons, because 11's an odd number, 8's an even number. I can't create an even from an odd. Doesn't matter how hard I try. So obviously in those scenarios, you're not going to be able to obey the octet rule. It's literally impossible to do so. There are 2 other scenarios. Hypervalency, going over 8 valence electrons. We've kind of alluded to this, the fact that it's a possibility. We're seeing it in the problem that we're working on right now, PF5. The only way that we can make PF5 is if we break the octet rule somewhere. The question is, when is it okay? And the answer, we have to have an element in the 3rd energy level or greater. So I've got to be starting at sodium and below, because I've got to have access to those empty d orbitals to make it possible. So from the standpoint of the problem that we're working on, fluorine can't break the octet rule. It doesn't possess the orbitals necessary to do so. So phosphorus is the only place that could take on those extra electrons. The third scenario, hypovalency. That is there a scenario where it's okay to have fewer than 8 electrons and not just because it's an odd number? And atoms are capable of doing this, but where we see it the most often is in the boron group. Now, regardless of scenario, the only way that we can break the octet rule in any of these 3 scenarios is if it is backed by formal charge minimization. If by breaking the octet rule, our formal charges suddenly become a lot better, a lot more manageable, we go from -1 to 0, we go from +2 to +1, we see improvement in formal charge, then we know that we're heading in the right direction, that we're doing what we're supposed to do. Classic example of this is BF3 for hypovalency. Boron trifluoride, BF3, to do the octet rule would require a double bond somewhere. I would need to have a double bond between boron and fluorine to do so. Problem is, from a formal charge standpoint, that would give the boron a -1 charge and the fluorine a +1 charge. We just went through why fluorine doesn't do positive. From an electronegativity standpoint, it definitely doesn't do positive. So by breaking the octet rule, by keeping all of those bonds single, boron trifluoride only has 6 electrons around the boron. But from a formal charge standpoint, it has a formal charge of 0. The formal charge stabilizes the otherwise odd scenario with regard to the octet rule. So we come back to our example with PF5. Obviously, this one doesn't work. It gets way complicated quickly. We end up having negative charges and positive charges where we shouldn't. Since we know that breaking the octet rule for phosphorus is okay, why don't we just break it in the simplest way possible? Simplest way possible would be going back to single bonds for fluorine to phosphorus all over the place. If I fill in the dots, and count it up, starting on top left, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. 40 electrons in the structure, matching the 40 electrons that are supposed to be there. From a formal charge standpoint, phosphorus, 5 valence electrons, no dots, 5 bonds, no charge. All of the fluorines are the same. 7 valence electrons, 6 dots, 1 bond. No formal charge there either. So we don't just break the octet rule for the heck of it. There has to be a reason why. And the reason why is apparent here with regard to formal charge. We went from a mess of formal charge, negatives on lower electronegative elements, positives on high electronegative elements, weird bonding structure, to a much simpler design with no formal charges anywhere. That's the whole point. We want to do that whenever possible. And so there are occasions where breaking the octet rule makes a lot of sense. And formal charge is always the driving force for that. Doesn't matter if we're breaking the octet rule by going too high or by going too low. Formal charge is going to be the driving force in either direction. So keep that in mind as you're doing some of those assignments, as you're doing that Lewis structure skill builder for lab, as you're doing your homework and your post-lecture tonight. Those are kind of the central ideas. Let's do one more example before we wrap this part up and do something else. Let's look at this one, I3 minus. Now, the formatting here is a little bit goofy. It should be the triiodide ion, I3 with a -1 charge. We haven't done a charged particle yet. How do we handle that charge? How do we handle that from a drawing standpoint? How do we handle that from a counting standpoint? Well, from a drawing standpoint, it's no different. We're going to treat it just like anything else. From a counting standpoint, I know that I have 7 valence electrons in iodine times 3. The charge, since it's a negative charge, that means we have an extra electron. 1 extra electron turns my 21 electrons into 22 electrons. So 22 electrons in total in my triiodide ion. Drawing this out, again, same kind of process. Iodine in the middle, simple structure, single bonds, fill out my octet. If I do this, I see 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. 20 electrons in this structure. I'm supposed to have 22. Now, we haven't dealt with this particular problem before. We've always dealt with the opposite. My structure has too many. I need to start adding extra bonds. When the structure has too few, remember, it's not that we add extra bonds. Adding extra bonds would actually mess up with our formal charge. What we do instead is we add more dots. In particular, we add more dots to the center atom, assuming that the center atom is able to break the octet rule. Iodine is a period 5 element, so yes, definitely can support the extra electrons. Where do those extra electrons go? They go right here in the middle. Where you put them doesn't really matter too much at this point. We're not really interested in shape or structure. We're just interested in making sure that we've got all the electrons in the right place. So now I've got 22 electrons. It matches up. From a formal charge standpoint, the iodine on the left, 7 valence electrons, 6 dots, 1 bond, no formal charge on that left iodine. Iodine on the center, 7 valence electrons, 6 dots, 2 bonds, -1 charge overall. Iodine on the right, 7 valence electrons, 6 dots, 1 bond, no charge on the outside. Okay, so I've got a -1 charge here. Is my formal charge minimized? Or do I need to start playing around with bonding and things? Okay, Aaliyah's made a really good point here. This is a charged particle. This is an ion. There's going to be formal charge somewhere. Remember, the sum of all the formal charges has to equal the charge of the species. So I've got to have a -1 net charge somewhere. It just happens to be on the center atom this time. So this is okay. In fact, this is exactly what we want. If I have a charged particle and the only formal charge is the place where that charge resides, I'm good. I don't need to do any more. If I have a multiple charge, like a -2, I'm going to see 2 atoms with a -1 charge. Formal charges above -1 or +1 tend to be pretty unstable. So if I have a -2 charge, that means I've got 2 -1s somewhere. If I've got a +2 charge, I've got 2 +1s somewhere, or I've got something ionic. Any questions about these Lewis structures?